I want to say first, thank you, Natasha, for the introduction, and thank you, Hussein, and the other organizers for putting this together. Amazingly, I know I'm kind of a young guy compared to some here, but I actually started ITAMP 17 years ago, if you can imagine that. And I've been in this auditorium, I would say not an absurd number of times, but perhaps more than my fair share. And I'm going to actually spend a bit of time today talking about some of the best parts of having been at ITAMP, and then I'll spend a bit of time talking about science. As is usually the case when I give a talk, I encourage people to interrupt me as we go. And I'm going to start by talking about my very first research project as a budding scientist. And it kind of went like this. So you can kind of reproduce this for yourself. You go to Google, you Google Jacob Taylor. There he is. It's a remarkable resemblance to the Jacob Taylor of 1997, for those of you who remember me from that era. Perhaps I was a little less brooding. I think I was less brooding. Also, I didn't have werewolf eyes, just so we're clear. But nonetheless, I was wandering the halls of ITAMP as a young undergraduate, having just taken quantum mechanics, and knowing that I really had to do this for the rest of my life. And I wasn't exactly certain what it was going to be. And I went to about 8 different researchers who had in their CFA booklet the word quantum somewhere in their description. And I think the 8th researcher was Jim Babb, who, when I wandered into his hall and I basically said, I want to do something, quantum. He's like, well, okay. I know Alex has some idea that he's been thinking about. Went to talk to Alex, came back, oh, there's a little bit of money. Well, I don't know, you took quantum mechanics, but maybe let's do some real quantum mechanics. So why don't you go read Schiff? And undaunted, I went away, and 2 weeks later I came back, okay, done. Not really realizing perhaps that there's so much more depth to that wonderful textbook than I had appreciated at the time, that I came back to it several times since then. And basically from that point, we started sitting down together to set up a calculation to do something that is the simplest non-trivial calculation you could do in molecular physics, which is the H2 plus ion, molecular ion. And we basically went into literature, searched around, and discovered essentially that what I needed to do was write a lot of fortran. And so that's what we did. There were many debates about Maple versus Mathematica during that era, which you may recall. But at the end of the day, through Jim's perseverance with a young student like me, we were able to do a very nice variational calculation at the time. And this is actually when I first met Zhang Chao and of course Alex, where we basically sat down together and I learned that doing things variationally is a particular tool in the toolbox. And what this taught me when we kind of were able to finally get our result about the dipole polarizability was that there are many tools in the theorist toolbox, and you want to choose first a good problem, and for that I'm indebted to Alex because he chooses good problems, and second, the right tool. And this particular case, there are many other groups that were doing the same type of calculation using tools that weren't ideal for the task, because that was the tool that they had. And it took us the course of a summer to build the tool that we needed. And from that, I've learned that you should always go find the best tool for your problem, rather than use the tools that you necessarily already have in hand. At the same time, I made a lot of friends. And primarily, this is because ITAMP has this daily tradition of the coffee hour, or minute, 15 minutes, 30 minutes. Sometimes it was only me. But nonetheless, I faithfully attended it and met a lot of really interesting people and made some great friends who I've kept in touch with for the many years since. And in some sense, I go through the ITAMP alumni booklet, and half of the people in the booklet are people that I've had long, intense conversations with. And so for me, ITAMP has always encapsulated the meaning of the AMO community. That being said, I wasn't entirely sold on molecular physics, so I took a brief foray and went into astrophysics for a little while. A few years later, I came back from Japan, came back to Harvard for graduate school, and I walked into Kate Kirby's office and I said pretty much the same thing. Just, I want to do something quantum. I've been doing black holes, I've been doing stellar clusters. I wanted something that, down at the angstrom scale rather than at the parsec scale. And Kate's immediate response was, well, there's this really dynamic young guy who just started a professorship who I think you overlapped with. And I said, oh yeah, there was that kind of crazy Russian theorist. What was his name? And I said, no, you should go talk to him. So she gave me some of his papers, and I went over to Misha's office, and I said, so you're doing really interesting stuff, it seems. Can I maybe work for you? Again, lots of fun things happened during that time. In addition to doing lots of great work with Misha, I met a number of other ITAMP postdocs with whom I collaborated with and still collaborate with. And basically, again, my community is being defined by the people who come through ITAMP. Since then, I'm now moved down to Maryland, where I'm at the Joint Quantum Institute, and we're now investigating sort of I would say the deepest questions at the boundary between understanding of quantum mechanics and understanding of nature. And towards that end, actually, I just wanted to highlight briefly that we've just started a new center, this Joint Center for Quantum Information and Computer Science, which is really trying to address some of the questions that I think were mentioned yesterday about what's the connection between our understanding of quantum mechanics and our understanding of the world. And we're interested, of course, in these questions about physics and chemistry and biology, which is what do we learn by having better quantum devices? Can we, for example, solve these ultra-fast problems that were mentioned yesterday? Can we solve new chemistry problems? Can we find new molecular problems that we have better understanding of than we do now? But also, you can ask the question about what physics tells us about computation. What is computable? What's easy for us to compute in a natural setting? And also, of course, what does computational complexity tell us about nature? There's some problems where if you're clever, you can solve it much faster than this sort of natural approach. And you have to ask, why is it that these other algorithms exist, but yet natural systems don't have them? And there's some more practical things, which is, of course, what gets this whole stuff funded, which is really the question, how do we keep secrets safe? And this is more tying back to my national labs connection, which is we, as sort of physicists, have created this wonderful set of technologies in this huge industry, the information technology industry, which at the moment, as an economic entity, is predicated on the ability to easily share secrets. And the wonderful thing about building a quantum computer, if you could do it, is that, of course, you will have access to the ability to factor large numbers and thus break all the codes. And the wonderful challenge from an economic perspective is you have to ask, how do I do e-commerce in a world with Shor's algorithm? How do I actually do national defense and national security in a world where there are no secrets? And so that's another key part, which is essentially these pieces together are the raison d'etre of this new center. And perhaps most topically, I've modeled this new center really off of the things I learned from ITAMP. And that is to say, we have some great postdoctoral fellowships, and we have our first crop of fellows coming in. I'm very excited about that. Of course, these are more computer science-oriented folks than they are atomic physics folks. We have some associated faculty, but in sort of two sides of the fence, computer science and physics. We have some workshops that we're going to do, but perhaps most importantly, a robust visitor program. So if you're interested in these questions, don't hesitate to contact me. Happy to have you come for a week, a month, or longer. So those sort of preparatory remarks out of the way, I'm now going to tell you some more technical stuff. The things that I've been working on that I find really exciting and intriguing at this quantum optics condensed matter interface. And you should understand that a lot of the things I'll be talking about, I learned the fundamental tools for these ideas as an atomic theorist, as a molecular theorist. But yet, at the end of the day, it's just a toolbox. You find another problem, where's the appropriate tool, and you can apply it, and it works beautifully. So, to give you a brief outline of my talk, depending upon time, I'll cover 3 topics. I'll first describe some basic pictures of photonics and phononics, and leave all the great interesting interesting stuff, I'll hopefully call it, with Peter's talk, because he's much more the expert in that. I'm more focused on a particular sub-challenge there. I'll then talk about how we do quantum Hall physics with light as a sort of test case for quantum simulation. And then, as time allows, I'll describe a little bit some of the ideas we have now for testing more unknown systems, many-body systems, and other systems whose quantum properties we don't fully understand, to determine whether our description of quantum mechanics is complete. But let me first talk about something very straightforward, which is photons and phonons. And this is motivated by the realization that at the moment in the laboratory, people have developed good quantum systems. Systems with a good quantum memory, where you can interface them easily, you can measure them, you can rotate them, but they're small. The Hilbert space they represent, the number of qubits they have, is finite in size, and it's hard to grow them. So you would like a system which allows you to connect these systems up, sharing quantum information between them. Now, it turns out that there's a direct application of this same idea in measurement, which is that you often have a weak signal coming in a carrier or a bandwidth or a frequency that's hard for you to detect. People who do astronomy run into this all the time, particularly in terahertz and in radio waves. And what you'd like is some type of transducer which takes the signal and converts it to a measurement system you can work very reliably in, and add as little noise as possible along the way. And it turns out that solving the quantum interconnect problem is analogous to solving the quantum transducer problem. And thus, in many respects, whatever progress you make on one is immediate progress on the other, and vice versa. Now, what is a quantum transducer? Well, actually, we're all familiar with one. I'm using one right now, except it's not in the quantum domain. It's a microphone, or a loudspeaker. It's a device where you have a voltage and a capacitance. As you move the parallel plates in the capacitance changes. And you have this connection between the change in voltage, which causes a change in capacitance, which causes a change in X, or vice versa. Now, this was actually used quite famously by the great inventor Thurman when he was, maybe Misha knows the true details of the story, but as I understand it, told by the Cryptological Museum, he was basically approached and said, well, can you build us something? We're making a gift for the US ambassador to Moscow. And it goes in the ambassador's office in 1948. It's this beautiful great seal. And about 2 years later, they've realized that the ambassador's office is bugged. And they sweep for bugs, and they can't find anything. And they sweep for bugs, and they can't find anything. They start disassembling everything. Eventually, they actually disassemble the walls, and they find inside this little box right here with a wire attached. And that little box is, in fact, a microwave cavity with a movable diaphragm. And this antenna, you can shine a radio frequency beam off of about 330 megahertz. The sound waves modulate the resonance frequency of this cavity, which produces a sideband on this radio beam, which when you bounce light off of it, comes back to you when you pick up that sideband, and that is transduced the phonon information into microwave information.
But this is a purely classical. Why do you want to say it's phonon?
Well, that's purely classical. What's amazing is that we've had now progress in phononics and photonic systems in these domains, where we get the system down to the point which I call the quantum domain, which is where the quantum dephasing rate, including the thermal load and all these things, is actually slower than the oscillation frequency. And so now, and really for the first time, people are building systems which are macroscopic oscillators. This is sort of 10 micron long by 1 micron wide kind of beam, which is oscillating multiple times before it dephases. And that you can build these things is actually a triumph of material science, but it also allows us to investigate now the quantum domain of these transducers. And I'm particularly interested in this because, as I mentioned, there's some things that are hard to detect. And one of the things you'd like to detect really well are astrophysical photons, in particular radio frequency photons. So if you have a Planck satellite, you are concerned about your cryogens. And that's because you're looking up in the sky, and the sky is 3 Kelvin, and you like your amplifier to be cold compared to 3 Kelvin. And the way you do that right now is with a superconducting amplifier. but your signal is narrow band. And it turns out that it's actually unnecessary to use a superconducting amplifier if you can do good transduction nearly at the quantum level. It doesn't have to be quantum transduction for this radio frequency application, but the key point is you have some antenna, and it's going to go into an optomechanical system which will convert the antenna frequency signal, which is in the gigahertz, up into the terahertz, where you can then use very high efficiency photodetectors for your signal. And the noise temperature added, it can actually be much, much smaller than 300 Kelvin, even though the system is operating at room temperature. So you really can start asking these questions. Can you make these things transduce without adding excess noise past the noise level of the signal coming in? The answer is yes. And then from there you start to ask, can you make actually a universal interface, an interface that you choose your frequency coming in, you choose your frequency going out, one in the radio frequency, one in the optical, and that allows you to connect, for example, an atom, which is resonant at 780 nanometers of light, with a superconducting qubit, which is resonant at 4 gigahertz. And that concept of the universal interface is using the connection between optomechanics, radiation pressure. So here's the radiation pressure interaction. I have an electric field squared times the position of the object. When I put a large pump field in the system, this is biasing up my system. I do the same thing in the microphone. That's why I have a power switch on it. I have the classical field and the quantum fluctuations, and the two are beating against each other. It's the dot product of the two, right? And that beating occurs at the optical frequency, which means this is a parametric coupling that can frequency convert a low-frequency phonon into a high-frequency photon. That's how, of course, you generate sidebands. So this is some optical cavity with, for example, a reflective membrane in the middle. As light goes through, the membrane oscillates, it generates sidebands of the cavity system. At the same time, electromechanics is a Hamiltonian in which the capacitance depends upon the position. So here's my stored energy in a capacitor, and you see immediately that I get an xq squared coupling. Here I had an e squared x coupling. I put a bias voltage on, this oscillating in time. That produces an oscillating classical charge on my capacitor. And so again, I can efficiently couple now a electrical circuit to the mechanical system. You put the pieces together, and you have an electrical load coming in, and this produces a versatile optical interface. And now, with the advancements in the field to get these systems down to the quantum domain, you can actually have an optical interface where an electrical signal comes in and produces an optical photon with no added noise. So there's some glimmerings towards this with our experimental colleagues over in Denmark, where at the University of Copenhagen, Eugene Polzik's group have built a device with the silicon-on-nitride membrane coated with some aluminum on top of a capacitor system. They hooked it up to a resonant circuit. They had an antenna in the form of an inductor, and they're able to measure that they're limited by the noise of their antenna system, and they can cool the antenna system down and see that they get down colder and colder temperatures. So they're starting to get to the point where we can think about doing this transduction. This stuff I find kind of fun, but what's really intriguing when you start working with phonons and with photons is that you have some control of what's happening in your system, and it's very particular. That is, if you recall what phonons are, you have some sort of crystal. Each atom is its own little harmonic oscillator, and they're coupled together. So, one moves, and the rest of the chain starts moving back and forth. Right? Those are the excitations of the system. In the continuum limit, you would call these things phonons. And the key point is that by controlling the structure of this lattice and the forces between them, you actually can control the nature of excitations in your system. So I'm going to use that concept in the next section of my talk. And in particular, I'm going to suggest that we can control the nature of excitations for light to induce a non-trivial topological order on the light. Now, you could ask, what does it mean, topological order? I've heard those words a lot, but let me remind you what's not topological order, which is the traditional paradigm of physics, which is symmetry breaking. So I have some system, here's my canonical Mexican hat potential, and spontaneously, I break the symmetry in the system. That produces an order parameter, which is a local description of this new phase. That produces the Higgs mechanism, that produces superconductivity. You get a wide variety of options. And that seemed to be the story, according to Landau. Now, Landau is a very smart guy, and of course he knew what he was talking about. It turns out, however, that there's some properties that you can't describe locally. And these are properties associated with the topology of the system. And in the late 1970s, early 1980s, people started realizing that you needed a better description of these types of order to include non-local order, topological order. This is a beautiful picture, which follows, by the way, the general premise of condensed matter experiment. The uglier your device, the more beautiful the data. So this is from the Densui, where they had their gallium arsenide Hall bar system. They apply a magnetic field to it, and they see this beautiful set of quantized conductance peaks as you go, which represents the addition of edge states in this system, because I have a system that at zero magnetic field is a conductor, and it is surrounded by a real insulator. Now I start increasing magnetic field. That's just adiabatically turning on this field. And the bulk of the system gets filled with these Landau levels, where the electrons are just cycling around in circles. When they're cycling around in circles, they're not going to conduct. But I have this boundary between the system, which is an actual insulator on the outside, and the system in the middle, which looks like an insulator locally, but I can't deform an insulator to a conductor adiabatically. Consequently, at the interface, I have edge states. I have skipping orbits where an electron hops around like this, and that allows the conductance around the edge of the system to happen, and it happens in quantized nature. And the key point here is that actually how many edges you have depends upon the topology of the system, if it's a sphere or a donut or a disk. And this topology matters. This, of course, is a very rich field with many different applications. There's extensions to the so-called topological insulators, which are quantum spin Hall systems, or in 3 dimensions. There's concepts that you can do universal quantum computing, fault tolerantly perhaps, using these ideas. There's extensions to the atomic systems, where you go from charged fermions to neutral bosons or neutral fermions. There's even questions about these so-called Majorana particles. What we were interested in was using this realization that we can control the meaning of excitations in systems to do this with light. And this is actually becoming, for us, a very intriguing thing and a burgeoning field. We had this incubator last month on topological order with light at the OSA. Physics Today thought it was kind of neat, so we've got some nice little pictures from there. But the thing you need to understand here is what we're doing is we're trying to recreate, redefine the meaning of excitations in our system. And towards that end, I want to remind you what our goal is. Our goal is to make the photons, which are neutral, and bosons behave like they're charged particles in a magnetic field. Now, Ian Spielman, Victor Glitzky, and a few others pointed the way with neutrals, with atoms. And the answer was spin-orbit coupling. What's going on? Well, you have to recall that the generator of translations in the magnetic field is not just the kinetic momentum, but it's the canonical momentum, P minus A. So I generate a translation of distance A like this. If I have translations over a closed path, right, it's just going to be the product of several of these unitaries. So that's this object here. You'll recognize this sum over paths, if it's a closed path, as just this integral around the loop. Right? Consequently, if this A quantity has a non-trivial curl, I get a magnetic field. Now, how do I generate that in practice? Well, I have some Hamiltonian with this p dot alpha term, where alpha depends upon position and has some other constants of motion attached to it. Or alternatively, if I make a lattice version of this where I've got hopping, and when I hop from a site to a site, I pick up a phase represented by this I, capital A, little a term, that should suffice to generate a magnetic field. It's a synthetic field. It's not a real magnetic field. And this is really the basis of what happens with the atoms, what happens with the photons. We're just taking advantage of this p dot alpha type term, where alpha typically has a spin degree of freedom in it, so that you don't break time reversal symmetry. So it's a spin Hall system, not a regular quantum Hall system. Put this thing on a lattice, and of course you get this beautiful example of the first fractal, one of the first fractals in physics, the Hofstadter butterfly, where you're looking at the transmission spectrum of a one particle system. So just, I try and put a photon in, and where does it go? Can it go through or not? You put it on a torus as a function of the frequency of the photon and the effective magnetic field you've applied for a uniform field. You get these bands of conducting states and then these insulating regions in the middle. These are sort of Landau levels down at low magnetic field, low flux filling, but then they sort of bifurcate into this beautiful fractal. One nice thing about doing it on the lattice is it's very straightforward to go to high magnetic field regimes where this Hofstadter butterfly has real structure to it. And the key point is this is on a torus, but on a disk, I have an edge. And that edge produces edge states. So there's to be a slight correction to that associated with the existence of an edge. And this is sort of like a topological insulator here, and it's separated by these conducting bands. We came up with some ideas how to do this with light, and it was inspired by some beautiful work using waveguides written on silicon chips, using commercial silicon technology. And so Mahmoud Hafezi, my postdoc at the time, and I started thinking about how we might do this, and then we had some great discussions with Misha and Eugene, which essentially led us to the realization that we could do this all with linear optics and waveguides. And the key idea is to realize that if I have a ring waveguide, which forms a resonance, a whispering gallery type resonance, I have a degeneracy, clockwise and counterclockwise. And I can assign that degeneracy a label, a pseudo-spin label of up and down. A clockwise photon going through a waveguide picks up a phase along the bottom, and then when it comes back, it goes along the top, and it can pick up a different phase, and I can control the phase I pick up by changing the relative length of the bottom section of the waveguide and the top section of the waveguide. Photons hop from resonator to resonator through these waveguides. That produces a tight binding Hamiltonian for the photons. And the phase you pick up as you go left to right or right to left is different because of the difference in length, which looks like this phase term here. If the term has a non-trivial curl, that is to say, I'm able to build a big lattice of these and the length difference changes as a function of the vertical index in the lattice, that produces a Landau gauge. This is a spin Hall system. If I flip from clockwise circulating photons to counterclockwise circulating photons, the sign of magnetic field flips. Conveniently, these systems have not that high quality factor. That means that they don't distinguish clockwise and counterclockwise light. The roughness and such is sort of overwhelmed by the additional damping in the system. Consequently, you can actually try and realize this. This is an example of a chip that Mahmoud had fabricated using silicon-on-insulator technology. This is the scale bar for the actual rings up here. This is a 10 by 10 array. The experiments were done in Al Migdal's lab with Mahmoud basically doing all the work. You put light into a waveguide coming in here, it goes through. This injects it in a clockwise fashion. It goes around, and it comes out the other side. You can actually look at the transmission through the device, and you can also look at the light scattered out of the plane via a microscope. And you get this really ugly image. And now my background as an astronomer comes in, and I say, well, I'm used to ugly images. I worked with HST data. I mean, come on. Compared to HST, this is easy. So we go and we do aperture photometry on these, and then reproduce another image which actually has integrated the light from each of these rings, which you can barely pick up here, into something that looks a little bit prettier. And so these reduced images are what you'll be seeing in a moment. In terms of the actual device, we sort of aim to fabricate it with about a quarter flux per plaquette. We got a little less than that in practice by fabrication, well, imperfections, let's call it. So you can simulate what happens if you inject light either at slightly lower frequency than the middle of the band or slightly higher frequency than the middle of the band. One produces a long edge, the other produces a short edge. Put it together, and you get this beautiful experimental outcome. You can also just remove a resonator from the system. And actually, what happens? Well, the light goes right around the missing device. Why? It's topologically protected. This has to do with the boundary of the system. If I deform the boundary, the edge states stay the same. By deforming the boundary, by removing one of the resonators, the light goes right around it. Of course, nothing I've told you is interesting. It's fun, it's pedagogical. But this is all one-body wave physics. You could probably do this with wine glasses that you rub around. You know, build a big array. We're talking about doing it that way just for, demonstration purposes. What we want to do to make it interesting is have the photons run into each other, have them interact. And towards that end, we take the advice of a kind of shady character from American Past, this guy Willie Sutton, who was asked famously, why do you rob banks? And of course he said that's because where the money is. But actually, he asked them slightly the wrong question. They should have asked, why do you use microwaves rather than light? And of course he would have said, that's because that's where the nonlinearity is. Though there is another alternative history in which you could ask him, why do you use Rydbergs? And he says, that's because that's where the nonlinearity is. So I'm going to tell you just for a moment about the microwave version of this story, and we'll leave the Rydberg version for the experts in the room. This is a slightly technical slide. Here is this hopping Hamiltonian we were describing before. And now what I want to add to it is a three-body interaction. Now, three-body interaction might seem a little non-obvious to you at the beginning. You should understand that if I want to do non-abelian systems, I want multi-body interaction. Now, I can do that by building it up from Coulomb, which is easy with electrons and hard with light, or I can do it by directly engineering multi-body interaction. In this case, it turns out we can do this with an array of superconducting qubits. These are so-called fluxonium qubits that are coupled by parametric couplers. The parametric couplers are the things that allow us to set the magnetic field. So basically, you can have a time variation here, which causes a hopping to occur with frequency shift. Changing the phase of the pump changes that. Again, technical slide. The other thing you want is interactions. It turns out you take a fluxonium qubit, which is basically a RF squid with a big inductor attached to it. It looks like a harmonic oscillator with a slight anharmonicity. But amazingly, this anharmonicity works out just so that you can have no two-body interaction, so two photons don't scatter off each other, but a strong three-body interaction. So three photons run into each other and are elastically prevented from running into each other. And this allows us to then start to approach the fractional quantum Hall regime. In my remaining 4 minutes, I want to now describe sort of the generalized many-body question, assuming you're able to do this successfully. What are you going to probe that proves to you that your system is actually doing something quantum? Because a lot of these things have classical phase diagrams that are also very interesting, but yet they don't tell you that you made a quantum phase. And towards that end, we've been thinking a lot about what the meaning of forces is. So think about two parties, Alice and Bob, separated by some reasonable distance from each other. And each of these parties is controlling a single harmonic oscillator. That's their sort of tool. And this harmonic oscillator interacts with some background, which here I call some field A. And Alice observes that when she wiggles her particle, Bob's particle wiggles. Right? That's a force law. It's communication. And of course, you can see that by generating sort of an interaction. Here is this gauge field, this particle interacting with the two positions. I do unitary transformation, which removes the gauge field. I get an interaction between the two particles, this type x1, x2. Right? This is something you run into all the time in field theory. You did it actually back in undergraduate E&M. This is how you get Coulomb interaction out of a local Maxwellian theory. Now, our actual goal is not just some gauge field here, but some arbitrary many-body system in between. We want to ask the question, when can we distinguish a classical force and a quantum force? And a classical force I haven't defined for you, so let me define it very clearly. Forces are a method of communication for particles. A classical force is a force that does not allow quantum information through. That's it. Now, there are many other ways people like to define classical. That's my preferred approach. So here's sort of what happens. You can imagine I've got Alice. Alice sends a virtual particle over to Bob. Bob sends a virtual particle back to Alice. Alice sends a virtual particle to Bob, et cetera, et cetera, et cetera. That's how a force law develops in all the field theory that we know. To prevent entanglement going through, you merely have to put in some hypothetical object, I'll call a screen, between these two parties. And that hypothetical object then is going to prevent entanglement from going through. Now you can test for the existence of this object. Or rather, you can test for its non-existence. You could say, if it existed, the following must be true. If the following is not true, then it does not exist. It's very much like a Bell's inequality. And in particular, the screen has certain properties. First of all, it's got to reproduce sort of the classical dynamics of the system, the Ehrenfest type dynamics of the system, which is that it's communicating, and you can observe that classically. But the other point, of course, is it can't let any entanglement through. And these two constraints together are actually tightly constraining. Sending classical information through dramatically limits the set of channels you can possibly have. And that allows us to make a very nice example case, which turns out to saturate the bound, I'll tell you in about a moment. So here's my hypothetical gauge particle. How do I make a screen? I do heterodyne measurement. Take it, I split it on a beam splitter. I have a local oscillator, another local oscillator. I pick up the x and p quadratures of this field. Heterodyne measurement. Happy for everyone. Of course, given those outcomes, I can then produce some coherent state which mimics what was coming in. But I can't do it noiselessly. And that's the so-called single photon vacuum noise added when I have an amplifier. There's a wide variety of such channels, but the key point is that we're able to show that if I have this Alice and Bob, if they interact with this observable classical type interaction, G, X, A, X, B, but I don't know if it's quantum or not, and Alice and Bob are getting harmonic oscillators, so they have these conjugate momenta, then I observe that there exists a variance noise bound, that the variance in the momenta is always increasing by a rate bounded by the communication rate, G, in the system. And so we're now extending this in the many-body case rather than just a simple harmonic oscillator case. But the key point here is that you can learn from the noise whether the system is classical. You can't learn whether it's, you can't really know, sorry, you can learn whether it's quantum. If I violate this bound, it could be still quantum and something else is going on. I've got decoherence, I've got noise, I've got thermal effects. But if you're below this bound in noise, necessarily your two particles were communicating quantum mechanically. And not only that, but we actually have a protocol from that communication which allows you to purify entanglement. This turns out to be a pretty technical result, so that we ended up having to write 3 papers on it. But sometimes things are hard, and that's how life is. So one of the things that we immediately saw before we did the many-body case is that this allows you to actually sort of make a simple test of the question, can I show that gravity communicates quantum information? Because we know that gravity should communicate quantum information. We'd like to think such a quantum theory of gravity should exist. And in fact, we can sort of produce a Gedanken experiment to test it, where you have the torsional oscillator, another torsional oscillator, and you observe the 2 torsional oscillators. One moves, and the other starts wiggling. Right? That's your classical communication. Put the numbers together. You use terrestrial properties of materials. Platinum turns out to be a pretty good one. Iridium's also pretty good. You have a pretty weak coupling. You get sort of 1 noise phonon every 3,000 seconds, which is an awfully hard experiment. However, as is the case for processors, in this case also we think if you can build these things using an industrial silicon process, which we think you can do, you can make it embarrassingly parallel. So each experiment takes at least 3,000 seconds. You need 10 to the 7 experiments. That's at least 300 years, for those of you who remember how to multiply seconds into years. But it's embarrassingly parallel, in the sense that if I have 10 to the 6 devices, that 300-year time scale goes down to a very small scale. If I even have just 10 to the 3 devices, I'm down to a year for integration. And so we think this is actually an interesting way, a hard experiment perhaps, but an interesting way to actually test whether gravity communicates quantum information or not. And so with that, I'll just conclude, and particularly just want to thank Mamad Hafezi, who's responsible for a lot of this topological work that you saw, and Prabina Hatikari, who's a student working on those projects, and Sunil, who did the experimental work, and then Devir, who is my theorist working on this last section, and Junong, who worked on the optomechanics along with Felipe Guzman Cervantes in the first section. Thank you for your time.
So about your second part where you show this experiment with edge state for photons. So how many photons are? I guess these are classical lights.
It's classical light, that's right.
So it's plenty number of photons, yes. Because I didn't see actually demonstrate the chiral nature. It's being on the edge does not mean it's topological. It has to be chiral. That means one polarizing going one way, the other polarizing going the other way. So could they already do this or not?
So the other injection, so you flip which ports you go into, so you put counterclockwise light in rather than clockwise light. For those devices, it doesn't work very well. So we can see it, but the data is not that great.
Okay, so that means this is still a geometrical sort of chiral rather than inherent
No, we think it's inherently chiral. However, the best evidence we have is that when we remove a resonator, that the edge routes around it, and that we have in many devices. So, yeah, go ahead.
Can I ask another? Okay, go ahead. Yeah, also the last part is very interesting. Normally, I mean, when we needed to detect a quantum or small signal, it's not just how small the signal is. Yes, it's the signal to noise ratio.
Yes.
That really matters. And of all the physical systems being considered, I think I only know two types of systems that can reach the classical limit. That means reach this short noise limit. Yeah, I'm not sure if solid state. Usually this is atomic clock systems. We know that in the world there are only 3 clocks that cannot reach this short noise limit. So, and then cavity QED in the optical regime, this is another system. I don't know how.
Actually, there's a third system, which is optomechanical systems. So the mechanics.
They already reached that.
Once you're in the quantum domain, then you get to this standard quantum limit, and you're indeed shot noise limited.
So that many groups.
What's that?
It's almost there.
Well, actually, it's done by about 3 or 4 groups now. Yeah.
I thought there was.
But there's still some residual 0.5 phonons or so like that.
Yes, but I mean, okay. So how deep into the shot noise limit we can debate, but you're.
So they are quite already close to there.
Yeah. Okay.
Yes. One very naive question. When you showed the virtual particles mediating the force in the last part, these particles which travel, they are not on Mars shell, or they are purely virtual. How do I measure purely virtual particles which are not real?
Well, you don't. What happens with the screen does.
You done an experiment that you would have your split.
Yeah. So I don't. Let's be clear in my sort of picture of pedagogy here.
Virtual particles.
This is a statement about if such a screen existed, what would happen? And so what happens is you add noise. What's the noise? It's converting virtual particles into real particles. Right? And your energy is coming from somewhere.
We have the right spectrum.
It's in fact it's exactly the same math as what happens in Hawking radiation. Right? The screen acts as a measurement device sitting between 2 halves of a system. And for the case of a black hole, that's of course the boundary of the black hole, and we have some physical reason to believe such a thing exists.